Uh, any questions? No questions. Okay. All right. So where were we, right? Before we begin, let's make two announcements. So the first one is we have a seminar this week, right? Usual time, which is 6 p.m., right? The speaker is Alvin Hong, right? He's the same person that made the notebook, right? That we've been using so far for the Yahoo Finance data. He'll be talking about delta hedging this time. Alvin will also teach a course, an elective course on application of math finance techniques to industry large-scale operation. I think we can ask him to talk about that during the seminar. His class will be offered next spring, all right? But the talk will be, pretty useful in terms of the applications, Python code will be provided, that kind of thing. The second is our second midterm, which, right, on the syllabus is supposed to be Wednesday. Sorry, our class meets on Thursday, right? So syllabus would be April 7th, if I remember correctly. Yeah.
I think you're sharing screen.
Oh, weird. I know why. You know what? I'm also on spring break, meaning that I forgot. All right. Wait, hold on. All right. Yep, spring break also got to me. Apologize. Thank you. Okay, much better. Right. I believe that it's for 7th or something, but well, because that's a Wednesday, right? That's a Thursday, which we want the midterm in class, right? So we'll change that to Thursday subtract 3, right? 4/4. Did I get the day right?
Yes.
Okay, awesome, thanks. So basically, right, so that week, right, but Monday rather than Thursday. So the content will be capped by the Thursday, right, of the week before, which is next Thursday. Will be, right, we'll know more details when we get there. Same format, right? I don't know, like maybe 2 theoretical questions, 2 coding questions, right? I haven't written the exam yet, right? But it's a very similar format, okay, to the first midterm. All right, so these are the 2 announcements that I want to make. Any question about any of these? Okay, so let us move on to the lecture, which is exotic options. So we'll be discussing exotic options for at least 2 weeks or so, maybe less. But so I will just summarize, right? The typical types which we have are vary options, right? Like up and out, up and in, down and out, down and in, right? Call put. So potentially we have 8 combinations, right? But as I explained before the break, that some of these may not make financial sense. the whole point of the barrier is to kind of, right, at least as far as I know, right, to limit the risk. So for example, up and out call would make sense because, right, you don't, as a option seller, kind of expose you to so by putting allow the above certain level, right, that would like limit your exposure, right? Same as down in call would make sense, right? And so on and so forth. We have the look back, right? Where basically the idea is a function of the max, right? Of the whole hash. So you could have a vanilla look back where this is just an identity function, or you could have like a look back call, right? Where this will be this minus k plus. Okay. And then we have the Asian, right? Where basically now the function will be dependent on, oh, sorry, the average, right? So here, right, the integral probably is a more fundamental object, right? Division by t is just averaging this out. So kind of, right, and also if you think about the barrier option, you see that the barrier option also relies on this running max process, right? Because when you cross the barrier, that means the max, right, has crossed the barrier as well. We'll talk about that. I mean, of course, if it's down, then it's kind of minimum rather than maximum, but you know, the spirit is pretty similar. So to recap, basically exotic options in some way is like the European option, but now you have the dependence, right, on some new process, right, like the running max or the integral. Okay. And understanding how these guys work will be part of the idea of understanding exotic options. But before that, right, let us kind of write down some remarks that we kind of wrote down last time that we didn't quite finish, I think, or, you know, we didn't discuss in depth. So the first one, right, is that exotic options are mostly OTC, right? So what that means is that they are not traded actively, right, on the market. There are not, I guess, a lot of supply and demand for them. And so two consequences, right? The first one is that we don't have something like Yahoo Finance or NASDAQ to look up their market price, right? So no readily available market price. So the liquidity, right, is low or none. But I guess the implication here is also that maybe, right, I'm not positive, but I think this is where QQuant, right, is used. In terms of pricing, right? Because when there is no market, right, when liquidity is low, then you have to use the tool of pricing, right, to come up with a price. Remember how I kind of harp on the idea that when there's an active market, right, like American option, okay? So by the way, European option also are mostly OTC, right? But we'll discuss that next. But basically, when there's a market, we do not pretend to use the pricing tool for pricing because we take the market price as given. But then, right, the pricing activities become deriving, right, implied information, okay, from the market price based on our model. For example, right, implied volatility or implied surface, right, implied volatility curve or surface, right, would be very useful, a very routine object that traders look at. Okay, but when there is no market, then, right, first of all, pricing is going to be important, because if you don't have a price, right, I guess the bank, right, the market makers, which are the bank, right, still have to, well, still want to sell these products, right, to some customers, right? That's why they're a market maker, right? They provide liquidity, but then what price do they price them at, right? That's exactly the question. But beyond that, right, pay attention, and this is something we do not have time or, frankly speaking, right, the resource to go into, is hedging, right? Because actually, it's not enough to come up with a price, right? A price is only for the market maker to give to the customer at the beginning, right? Basically, the customer gives them a bunch of cash, and then the bank or the market maker is exposed to, right, risk. So they must actively trade in the market, right? And that's their job. That's what they get paid for, to somehow hedge away the risk, right, involved with the exotic option. But hedging, right? And well, so probably, right, you can say that one can start with basic delta hedging, for example, and then, right, think of more sophisticated things. But, right, hedging is a very expensive in terms of, right, computational power, right, process, also imprecise, right, a lot of things to discuss. So therefore, right, I would say that we kind of just focus on the pricing part and leave the hedging part as implied, meaning that it's there, right? It could be done, but there are a lot of things, right, to be discussed. So just keep that in the back of your mind, right? Questions so far about this?
I have a question.
Yeah.
Can you clarify what is Q quant?
What do I mean by Q quant?
Yeah.
Oh, okay. Remember Dan Peugeot's talk about Q quant versus P quant? So this is a market terminology that you might want to know. So Q quant is what you guys are, what our program is. So basically, the Q, right? I know in our course I tend to use P tilde, but in a lot of textbook, Q is used to denote the risk neutral probability. So that's why Q quant is the one that basically use risk neutral to do stuff, right? So and of course, right, I think we had some discussion about what risk neutral probability is, right? I mean, why we use that, etc. But ultimately, right, one of the message about risk neutral probability is what? It's not, right, our world. It's not the physical probability, right? So P here is the physical probability. So there are reasons, right, why we use the Q point of view to price and to do hedging. But, right, there are other areas of finance that makes no sense to use risk neutral point of view, namely, for example, risk management, right? Because actually, even at the level of wording, right, when you do risk management, you definitely don't want to be risk neutral, because that's the whole point of, right, doing risk, right? So there are many areas, but one area that you guys may be immediately connected with is credit risk, right? What is it called? The quantile measure, value at risk, VAR, right? VAR, that kind of thing. So that's one area. Another area is actually so basically, right, here, this will be the market maker, sell side, bank, investment bank, The reason is, right, again, you see why. The reason is, they have to price stuff, right? They have to price stuff to sell. So again, right, that's why the Q quant. So risk management, right, also exists in banking stuff. That's definitely there. But like not in terms of hedging, but in terms of credit risk, right? How are they exposed to default, right, and that kind of thing. But so maybe let me throw it there, right? Default. That's more like the kind of risk we think about. But another area is the buy side. So buy side, right, would be hedge fund, portfolio management. So here, I would say that is probably also intuitive why, right? They don't care about the Q side, because here they care about, right, kind of profiting from the market up and down and behavior as a market, which, right, you probably want to work with the real world rather than on a risk neutral point of view. Also, right, buy side implies that they are buying, right, products from the sell side, so they have no business in terms of pricing either, right? They're a price taker, right? Of course, right, that's why P-quant sounds, because of this, P-quant sounds more sexy, right, than Q-quant, because they probably get involved with these folks, so who knows. But anyway, right, so here, time series techniques, right, things like that, machine learning, who knows, would be on this side. So yeah, I think Dan Peugeot, right, in his talk did kind of touch on this. So if you want to look at his point of view, you can go back to the talk in the recordings and take a look. Okay, so there's that. So yeah, our program is mostly known for discussing Q-quant for obvious reason. We have some courses on risk management, that kind of thing, but right, most of our program is focused on that. All right, any other question? Okay, so the second one, right, is Euro options. It might be a little bit surprising, but Euro options are also OTC mostly. This is at least this is what Alvin told me, and I think he used to trade, so I don't see any reason why he would tell me something wrong. But so basically, what you see, right, in Yahoo Finance and Nasdaq, etc., is American options. I think, again, right, I use the word mostly because I am not 100% sure, but I am 95% sure that these are the case, right? So maybe let's ask the question first of all, right? Then does that mean that also then Black-Scholes, is this why Black-Scholes formula, right, is so useful? Because we need to price European options. Why did we kind of not even emphasize that when we study European options? Why did we immediately look at like implied volatility and that kind of thing and neglect the pricing? Right? We don't have European option price, right? So why don't we price it? Do we? Do we have market price for European options? And by Euro options here, I kind of mean call and put, right? I don't mean some more like advanced option, like some more like well, there are not many more advanced European options, like the fake lock ST, right? That's some theoretical stuff, right? But of course, that can also be priced. But I'm talking about call put, more or less. So what do you think? Do we have market price for European options? Do we need to price it?
We have the call European option price, which is equal to the American call.
Exactly, right? Of course we do. So first of all, right, Euro call is equal to American call. This is a fundamental relation that anyone who takes any course in option pricing must know. And like I said, right, we will explain that later. But so that takes care of it because, right, if this is the case, then when you look up the market price for American call, that means you look up the price for American European call. But then, right, when we go to the put section, right, on NASDAQ or Yahoo Finance, that would be American put, right? And I will tell you that American put is more expensive than European put. So what does that leave us? That means that we need market price for European put, right? So, sorry, that means we don't have market price for European put, right? That means we need to use our pricing model, Black-Scholes, that kind of stuff. Is that true? What do we do with Euro put?
I think we can just price the forward and use the put.
Right, right. For Euro put, we just use put call parity because the forward requires no model, right? The forward, so call minus put, right, equals to forward, and the price of forward, right, let's say at time 0, right, is this, right? So you know the market price of the stock, right? Now, someone may say that, well, right, we don't know what this guy is. In reality, you can kind of use some bond discount to do this. So basically, right, that's why even though Euro options are OTC, they're OTC in the sense that people don't sell them actively on the market, but their market price, right, are readily available because of these relations. Okay, so the pricing activity starts with exotic options. Okay, European options, we use the model, right, to derive implied information, but we don't really need the pricing activity, right, for sorry, we don't need the model for pricing itself. Okay. All right. Questions? All right. So those are just like some good information to keep in the background. The third is actually now, right, about the pricing itself. Pricing, right, for exotic options, even under Black-Scholes model, right, which is the simplest model you can think of. And I know you guys, some of you are already kind of itching, right, to go beyond Black-Scholes because you claim, right, that the market don't use Black-Scholes that much. I might disagree there, right? Again, when I first learned Black-Scholes, I also think that that's a lame model, like people use more sophisticated ones. But the more I talk to practitioners, the more I feel like they tend to rely on Black-Scholes a lot, at least, you know, on the first try, right? Trust me, I mean, not trust me. I tend to find that people, you know, are reluctant to go beyond Black-Scholes unless they have absolute reasons to. This is not to say that they don't do that, right? But a lot of activities can be at least, you know, start out with Black-Scholes first to see what happens. So there are reasons to study that. But anyway, oh, believe it or not, binomial model are still used in the industry. So, you know, so there you go. So anyway, right? But the point I want to make is this, right, is complex. Meaning that, you know, analytical formula may not be available, right? And even if they are, can be quite tedious to derive, right? So exactly, a lot of our effort will be trying to explain some analytical formulas, right, that we'll be using in pricing exotic options. Okay, so some of the discussion will go into there. Now, this leads to two things, right? First of all, it leads to the explanation of why you want to kind of spend some time understanding analytical formulas. But then, right, someone may ask, well, why not in this day and age, right? Do Monte Carlo simulation, right? Because computers are so available that, right? We just do it. The appeal of Monte Carlo simulation is what? It's so easy to implement, right? You just write down what you see and then you take the average. Except, right, that this week's homework, I hope would convince you a little bit that Monte Carlo simulations, at least if you do naive, right, meaning you make no improvement on your Monte Carlo simulations, you have no hope, right? So the conversions are very slow. Why? It's easy to see, right? Because you have to simulate the whole path, all right? And when you take the average, the error, right, is 1/n. So that means you have to simulate a lot of path, right, to cover for your error on the 1/n. And then, right, each path themselves have their own errors for discretization, okay? So I will try to convince you with more homework on this. So even with today's power, right, computer power, on a personal computer, I don't think you can hope to get to any reasonable accuracy with Monte Carlo simulation, at least naive one. To give you, right, so another appreciation, let's go back to this, right, pricing. Like I said, right, pricing actually is just a starting point, okay? What people care about probably is also hedging. Now you think about what hedging implies, right? So if you do hedging, that means you want to calculate the delta, right? What is the delta? Delta would be the change in, right, stock price divided by the change in stock price. The change in the option price, right? Divided by the change in stock price. Yes. Now, if you do Monte Carlo simulations, right, to find your delta, that means that, first of all, right, I already claimed that pricing itself, right here, this guy has a lot of errors. And now, right, you do pricing here, divided by the simulation here. This guy will be highly unreliable. Do you understand? So already the V itself will be hard to capture accurately. So this is actually this is the point of numerical analysis 1, right? I hope you learn something like that. Basically, the more approximation you do, the more error you accumulate. So therefore, right, pricing is dubious, then forget about delta, right? And that kind of thing. That explains 2 things. First of all, that explains the work to find analytical formulas. Why? Because analytical formulas is exact. So from analytical formulas, if you try to use analytical formulas to approximate the delta, then you only make one kind of error, right? The discretization error at this level, which is small. But if you do simulation here, then this is hopeless, all right? Second is actually, this also explains why you want to pay attention to, I don't know if Casper does this, but any other technique, right? So basically, when people talk about Monte Carlo simulations, people don't talk about naive techniques, right? They talk about advanced techniques to speed up, right, your conversions. And this is the whole point of like taking an advanced course in this kind of topic, to know how you can, right, make the conversions faster, all right? So that explains, right? So the need to study more, right, if you want to use this technique. And that also explains why analytical formulas are still valuable, right, in this day and age. The second point I want to make is, right, also this also explains the PD approach, right, to pricing. Now, before, right, we talked about Black-Scholes PDE, but I was trying to sell Black-Scholes PDE as a relations of the Greeks, all right? Now, that's okay, right? That's the financial look at, things, right? Basically, Black-Scholes PDE tells you how the Greeks, right, behave. First of all, right, in exotic options, the Greek will not look exactly like the Black-Scholes PDE. Right? It looks similar, but it's different. You'll see, right? But another point is that now, right, with the exotic options, the PDE will no longer serve as just a relation between the Greeks. You can look at it like that, but it serves a more practical purpose. It tells you how to do pricing. It gives you another way to do pricing, right? So there are basically three ways to do pricing: analytical formulas, multi-color simulations, or PDE. Now, what do we mean by PDE? Of course, we mean numerical PDE, right? And this explains why, for example, numerical techniques are relevant in this area, right? Basically, so basically you have to spend effort, right? If you can derive this, great, but sometimes it's impossible to derive, right? Then you have to think of numerical techniques. But then, right, if you know more on this side, then you can use some efficient techniques, right, to price faster. If you know more on this side, then you can use some efficient multicolor simulation techniques to price faster, right? And I think until this day, there's no clear winner on either side, right? This guy is notorious for kind of hard to understand, I guess, or you have to kind of train yourself to know what it talks about. This guy is easier to understand, right? A little bit easier, but maybe slower, right? So if you need to learn more advanced techniques, and it's unclear, actually, I think, on how fast this can get. So all on, I think there's no clear winner on these approaches, okay? And of course, again, right, this guy may not be available, so forget about it in general. All right, so that's the things I want you to keep in mind, right, when it comes to exotic options. Any question? All right, so wow.
Can I ask a quick question?
Yeah, go ahead. Looks like
so for numerical PDEs, are there like certain methods that they use, or is it like on MATLAB, for example, they will use like a ODE command or something similar to on Python?
Okay, right. So what you're asking is something along the line of, it's always there, package versus custom code, right? And I guess this is why, right, MATLAB tried to sell their software, because they claim that, right? Oh, by the way, a lot of numerical analysts work for MATLAB, right, to optimize their package to the level where, right, I guess it's very, very fast or something like that. Now, how to say this, right? I think nothing wrong with package, right? If you take some Coursera stuff, right, even on machine learning, you will see Andrew Ng, right, the professor from Stanford, also uses MATLAB package, right, for some of his code. On the other hand, though, my take is that if you want to use a package, you must know what the package can do, right? What the parameters of the package are, what setup, right, you can use for the package. Now, Kareem, right, notice that what you were saying was ODE, right? And which is right. We talk about PDE, right? So from PDE to ODE is one step, right? So you can think of somehow, right? Again, transfer the PDE into a lot of ODEs, for example. But that's one thing, right? That you have to somehow convert your setup to the setup that the package can use. And by the way, if you take that machine learning course from Andrew Ng, you'll see that a lot of times that's what he does. He has to somehow be careful, right, to transfer his algorithms to the algorithms of the package. But the second one is more along the line that, custom code, right? A lot of the PD that we'll talk about is a little bit customary in the sense that it's on a customary domain, right? You have to specify the domain. And you have to specify the boundary conditions in the domain in a customary way, right? So basically, all these have to do with what kind of options you're dealing with. Now, I'm not so sure if the package is customizable to that level, Again, right, MATLAB may claim that they can do that, but that means that you have to dig into the documentation to learn what they can do, right? So, and then there are people who claim that their custom code can even beat the package. God knows, right? So that's all I can comment on this. Basically, there are people working on, you can find people working on all sides of things like this, right? Numerics, I feel, right, also tries to do some of their custom code for some of the, right, the work that they do. Only for the reason that, right, the package cannot be readily deployed, or maybe in their custom code, they deploy some of the package to do some of the custom work, all right? But when it comes to custom code, I think Kareem also mentioned some of the words here, but the two, at least the two basic elementary, right, approach that you will learn is finite difference and finite element, right, method to solve this. And then this is just two sub area, right? Within each of this area, there are tons of like different, you know, algorithms to approach them. So yeah, I don't have a concrete answer to Kareem's question. My answer is that people probably try to do both. My approach, because I am in academic, I don't care about efficiency so much. I tend to write custom code because I'm too lazy to look up package. But in real life, right, I do believe that MATLAB people who I spoke to claim that companies still use their package, a lot of them in the industry, right? MATLAB claims to be relevant in this industry. The reason, right, and I asked them why in this day and age, right, they have Python and that kind of thing, why can they still sell their product? They say that they stand behind a package, meaning that they claim, right, that they can be responsible for their numerical package. It does what it does, right? While of course with Python package, right, it's free, so you cannot find anyone to be responsible for that. And B, right, that means that the package can still be highly useful, right? Otherwise, who would use them? So there you go. But I just find myself being lazy, right, to understand what the package is. But I guess if you go out and work, right, in the industry, if that's your task, then you better spend time learning about these things. So yeah, that's my best answer to you.
Thank you.
Yep. All right. Any other question? All right. So so let us, right, start with some preliminaries, right, to study exotic options. So now we'll go to the theoretical side, right? So by the way, right, I hope you know what I'm trying to sell in this class. In this class, I try to sell you the context, right, the financial understanding, and some, right, numerical approach. But of course, right, I'm not responsible to teach you any of these, right? You will learn it, you want to learn it from other professionals. So when we do this, right, basically it's theoretical approach, all right? So we're doing theoretical understanding of these things, mostly. So where are we? All right, so the first one is the idea of stopping times, which I hope you have seen in Casper's class, you know, Math Finance 1, but it's worth it to review a little bit and try to tell you, right, how they're relevant here. So first of all, right, for one thing, notice that I kind of have not been so, like in particular, right, about filtration, right? The whole idea of FT, that kind of thing, you know, so far. The reason is we have been doing European options, right? It's really two time points, big T and then little t or zero. Doesn't really matter. They look kind of the same, right? So basically, so far in this class, we have no reason to look at time so much yet. Things will change from now, right? Because with exotic options, it's the whole path. So there are reasons for you to track the movement in time. Even with American options, right, it's the same thing, right? American options require you to look at a time where you want to stop and exercise the option. That's stopping time, right? So time will be something that we need to pay attention to from now on. Okay, so that's one conceptual change. So we definitely need a filtration, right, in the back of our mind now. And again, right, filtration for us is just information, right? Filtration is just the amount of information available at that time, okay? Now, tau, right, which is a random variable, a positive random, a non-negative, it can be 0. All right, is a stopping time, okay, with respect to some filtration, with respect to some set of information, right? Because with now you have to specify what kind of information you have. If so, first of all, let me write down the technical definition that you always see in any textbook when they discuss stopping time, and then I'll explain the English for it. Okay. So here, this is what they always write down. The event, right? Tau less than or equal to, so this is true for all t, all right? The event that tau is less than or equal to any time, small t, will belong to that filtration, right? Will belong to that sigma algebra, okay, at time t, time little t. All right, believe it or not, this is very, very mysterious, right? What the heck are they saying? So in English, what it says is this, and it's much more friendly. It says that we, at any time, we know whether tau happens or not by t. All right. So what do I mean by tau happen or not, right? Tau is a random variable. So for one thing, I hope you kind of see that, right? When we look at time, it's not enough for us to look at deterministic time, right? What do I mean by deterministic time? Like 12 o'clock, right? In the afternoon, that's deterministic time. 9 o'clock in the morning, right? That's deterministic time. What's a random time, right? A random time could be the time I walk into this class, right? I mean, I don't walk into this class exactly at 10:20. I walk into this class at some time, right? Or if you want the time that the earthquake happens, the next earthquake happens in California, right? That's a random time, okay? Now, so basically a random time is associated mostly with an event. That's the most natural way to think of it, right? So by tau happen, we mean that event has happened, right? Tau is mostly associated with an event. Second of all, right? So at any time, by tracking the filtration that we have, right? Okay, so I guess by observing, right? We need to also look at the information we have, right? So for example, if let's go back to the example that I walked into this class, right? If you sit in Hill Center, then the information you have is Hill Center. Then the event that I walk into this class is not a stopping time for you because you have no idea of when I walk into this class. But if you sit in this classroom, then the event that I walk into this class is a stopping time for you because you can observe that I walk into this class or not. Okay, so the information is a part of the stopping time for that reason. Now, same as earthquake, right? So earthquake is a stopping time if you can observe the proper information because by the time the earthquake hits, you should know it or not, right? Presumably if you're in California. So that said, right? Something is notoriously not a stopping time. And in the pedantic way that we look at things, right? So let me give you, right? Usual example of stopping times. So when you have a filtration, right, you can kind of think that FT is generated by some process. Generated, right? Let's say by some process, let's say by WT, right? So what that means is that, by observing the path of WT is the same as observing FT, right? Then the first time that WT does something, is usually the stopping time. All right. Now, you can generalize this to a less exotic example. So basically, the first time that something happens is a stopping time. Like the first time that I meet you as a person is a stopping time, right? What does that mean? So let us write down a more concrete, right, math. So usually you see something like this. The first time in FEMA, all right? Let's say that WT is bigger than, let's say K, all right? Like this. Okay. So what does this mean? This means that this is the first time that the Brownian motion crosses, right, the level K. All right. So this is a stopping time. Sorry, I should not abbreviate things. This particular one, with respect to the Brownian motion generated by that, sorry, the filtration generated by that very Brownian motion, right? What that means is if I observe the Brownian motion path, I would know when is the first time that the Brownian motion has crossed a level K, right? Let's demonstrate. Again, if you take a stochastic analysis course, then you will have a very fun time trying to dissect this object symbolically and prove it, blah, blah, blah. But a lot of times it's just a little bit futile, a little bit frustrating. So a picture can hopefully demonstrate a little bit more intuitively, right? So you have the Brownian motion, right? And so here, the Brownian motion does whatever it does, right? So you keep track of it. Now, suppose, right, this is the first, this is some t, right? What do you know? Well, you look at the path. Has it crossed level K yet? No, right? So here tau is definitely bigger than t, right? At this point, tau is definitely bigger than t, which is fine, right? Because the first time we know whether it happened or not, right? So being a sigma algebra, the complement of this also is in the sigma algebra, right? The complement means tau bigger than t, right? And then you keep track of it again, right? And there's some magical moment, right? So like that, right? So again, there's some maybe, let me throw the equal here. I'll explain later. It's just some technical thing. For example, right, at T2, right? Or let me maybe move the T a little bit further, right? Here's T2, right? And there, right? So at T2, do you know if tau has happened or not? Well, you do, right? Why? Because remember, right? The filtration collects all information up to that time moment. So therefore, right, at this time, if you have observed the path, you know that obviously this has happened, right? Tau has happened, right? So this is true, right? So you can do that, or you can do that, right? So that's clear, right? So the first time, right, that the Brownian motion crosses can be known by tracking the filtration. All right. So you're like, okay, that sounds too simple, right? You're making a big deal out of things. Maybe, but here's something that you see that a simple change to this will make it not a stopping time. All right. So the reason why we kind of analyzed the previous example is because of something like this. Let me change one thing, right? And maybe I'll try, instead of soup, let me write max, just because, just to make it easy for you, but you know, it should be a soup. All right. Now, again, right, when it comes to these things, you should try to say it out in English. I find that very helpful. Like, look, staring at symbols sometimes is really hard, right? So what this says is the last time, right, that WT crosses, right, level K. All right, because it's the max, right? The max of all the time, right? The max of all T, such that this is true. All right. Oh, by the way, maybe let me tell you in case you find it hard to read this, right? So the Brownian motion, right, clearly. So here in this picture, suppose it goes again, right here like this, right? So here's tau, right? Basically, the Brownian motion can cross again, right, at a level at a different time in the future. Yes, because there's no reason why the Brownian motion only has to cross once. But if it crosses multiple times, right, like this, then here, this is saying that then this is the first time, right? This is tau. This is not tau, right? Because this is the second time it crosses. Yes. And by the way, this is not crossing because, it is bigger, right? So, how do I say this? Oh, it could be also here. Yep, right. But anyway, right? So, no, it cannot be. Sorry. Because you take the minimum, so the minimum doesn't go here. So either here or here and then some further time. But this usually means cross up. So basically what I'm saying is like, there could be multiple points of crossing, but here, right, is the first time, all right? These don't count. These are not tau. Anyway, right, so the last time. So let's take a look at the picture, right? So what does that mean? Let's say, right? So here's a level K, right? And suppose that we have a path like this, right? So there, like that, right? So this is the first time, right? It crosses. And suppose that, right, the Brownian motion never goes up again. Right? Suppose that's the case. If the Brownian motion never goes up again, right, then the last time, right, that it's bigger or equal to K, right, would be here. Is that okay? Right, if the Brownian motion never goes up again, then the last time that it's bigger or equal to K is here, right? Now, why is that not a stopping time? Right? Why is that not a stopping time? So here, right, the first time is bigger or equal to K is here, the last time is here in this picture. Why is that not a stopping time? It's not a stopping time, right, because it violates this principle that we know whether this has happened or not by observing the information up to time t, right? So let's take a look at this picture, right? Let's say by this time, right, do we know whether tau has happened or not? Where tau is the last time, right? Well, you don't. Why not? Because at this moment, you need my knowledge, right? You need a crystal ball, right? Basically, some fortune teller to tell you that this will never happen again, for you to know that this is tau, right? If you're honest with yourself, this, right, at this point, you don't know, right? You don't know in the future whether the stock is gonna, cross up. Sorry, not a stop, right? The Brownian motion will cross up again, right? And so this is not a stopping time. Now let's take a more mundane example, right? It sounds a little bit kind of dark, but if you take any activity in your life, you don't know if this is the last time you do it, right? Because something might happen that, let's take, for example, you meet your friends, right? You may not meet that person again in the future because that person moves to another continent that you never visit. Let's take an easy example like that, right? So the moral of the story is just simple, that the first time you do something, you definitely know it, right? The first time you take an exam in kindergarten, whatever, you know it. When is the last time you take an exam? God knows. Maybe you take class when you're 70 years old, right? So a last time of something is never a stopping time, right? So stopping time, okay, so maybe first of all, so is this okay? It's just a crash course on stopping times. I want you to keep these examples in mind and know what a stopping time is, right? All right, so stopping times will play an important role, all right, in the analysis of barrier option. All right. And of course, American option too. But we'll look at barrier options first. So let's take the up and out, right? Which is our main example. So an up and out call will have this formulation, right? You will get paid like a call option if, right, you never cross a level L, right? That's specified by the contract. All right. Now, how is this connected, right, with a stopping time? Where does that come in? It comes in like this. It comes in like this. Exactly if I define tau as a first time that the stock crossed a barrier, right? Cross L, right? So again, right, trust me on this, that is a stopping time. Maybe just the equality that seems a little weird, but you know, it is because of infimum and a bunch of analysis, but this is a stopping time, all right? Is a stopping time with respect to the Brownian motion. Now, something I want to explain also is, right, why W and not S? The reason is, right, because here we assume that our stock is entirely generated by the Brownian motion, right? We're on the Black-Scholes model. So our stock is entirely generated by the Brownian motion. So by observing the Brownian motion is the same as observing our stock. So we would know exactly when the stock crosses the barrier, all right? Also is this stopping time. So for one thing, you could just rewrite the above as this, right? It's not a big deal, but like that, okay? So, right, to say that the max is less than or equal to L, right, for the entire path means the first time you cross L is after T. Does that make sense? So first of all, right, I can rewrite these two events like this. Okay, so that's one clue for the connection for you, right? So what I'm claiming is these two events are the same. Right? Where tau is defined like this. But more importantly, right? So that's not the only reason why we look at it like this. More importantly, right? At any time, let's say we look at VT, right? When we look at VT in the up and out call, right? The value of the up and out call barrier option at any time little t, right, will depend on the event tau less than or equal to t, right? So again, right, let's just speak about it in English. This is the first time that the stock has crossed the barrier L. When I look at the value of my up and out call option, clearly, right, it depends on whether this has happened before T or not. Right? In other words, if this is true, then VT will be
0.
exactly, right? And if this is true, then VT is, you know, positive. Who knows what that is? But right, but this, right? So in other words, you see this one single stopping time is connected to the entire value process, right? It's not just connected to the last payout, right? It's connected to the entire value process, okay? Okay. Now, the next is a discussion on we derive the PDE, right, for up and out call. All right. So it depends on several ingredients like this. All right. So first of all, all PDE we derive, including the Black-Scholes, right, will come from the martingale principle. What this says is the discounted, right, option price is a P tilde martingale. Is a risk neutral, right, martingale. But we need some modification. I'll explain. All right. So first of all, right, let me just discuss this, right, at two levels. At the technical level, what happens? At the technical level, right, this allows you to write down the PDE. Why? Because when you do this, right, e to the minus RT dt, right, at the technical level, you will apply Ito's formula, all right, to the discounted option price process to decompose it into something dt and something dwt. And because it's a martingale, then you're allowed to say this must be 0. And that's where your PDE comes from, all right? So that's the technical part of this principle, meaning that by being able to conclude that something is a martingale, you are allowed to conclude that the DT part, right, the drift part, right, the non-noisy part, right, must be 0. So therefore, you can write down your PD that way. Financially, I just want you to always remember that this is not a fancy notion. It just means the current price, right, of the future asset. Sorry, not the current price, the fair price is current price. What do I mean by this, right? What I mean is this, right? The fact that it's a martingale means that this is true, right? Or more generally, this is true. Right? They say the same thing. But, right, what is this, right? Don't look at this mathematically so much, but look at it as its meaning, right? This is a pricing equation, right? It tells you what is the fair price. So this side is a fair price, right? This is the fair price of the future payout, right, of the asset. Why? Because you discount it to a present value, right? And this is the future payout. And right, so same thing here. And this assert, right, by the martingale relation that it must be the current price. which again, right, is something very obvious, but that's why I say, right, the equation sounds fancy technically, right? But the interpretation financially is just this principle. All right, any questions so far? All right. So now how do we apply this principle, right, to up and out call? We apply like this, right? We will say that the discounted price of the up and out call is a martingale, but not quite, right? That's the modification part. Where does the modification come from? The modification comes from this, right? With, right, up and out call, we have the discounted, right, option price, which is the up and out call, is a P tilde martingale up to time tau. That's the key. That's the key modification. Again, what is this time? This time is the first time that the stock crosses the level F. All right. So how is this different from before, right, to the European option? To the European option. So basically, right, what this means is this. So roughly speaking, right, they'll say that this is a P tilde martingale if T is less than tau. That's what is really roughly, all right. I mean, this is in quote because mathematically tau is a random time, so it's a little bit awkward to write down precisely, but intuitively, right, it's not that hard. So, right, why is this a big deal, right? Before with the European option, right? With European option, then you have this is a P tilde martingale, no matter what, basically for your entire duration, right? This is an exploration. Here is a martingale as long as you have not crossed the barrier yet. All right. The discounted option price is a P tilde martingale as long as you have not crossed the barrier yet. So, right, as long as the barrier was not crossed. All right. Now, why is this true, right? And how does that affect anything? I'll explain that. But basically, first of all, right, let's try to explain why is this true. And that really comes back to this observation right here, right? So imagine, right, some point in time, and suppose that, right, by observing this, the filtration, you know that the stock has crossed the barrier already, right? So here's the barrier L, right? The stock starts somewhere here, and right. So let's say here's T, right? So at this point, right, you know that the stock has crossed the barrier. Then if someone asks you, okay, what's the price of the option now, right? So here's big T somewhere here. You must say, well, it's 0, right? On the other hand, if it's not crossed the barrier yet, like this. So someone asks, well, what is the price of what's the fair price of the option now? What do you say? Well, and what is that person asking? What that person is asking is exactly something like this, right? What's the fair price of the option now? And you will say, well, whatever its current price is, because it's still alive, right? It's still alive until, right, that time has been crossed. All right. So this actually is not, again, you can prove it kind of complicatedly mathematically, but what it really says is that as long as you're still alive, then this principle still holds. The fair price of the future payout is its current price because the option is still alive. All right, that's all. Now, let me quickly write down one more, which is this. That VT in up and out will just be a function of T and ST. And let me say this, right? You don't want to neglect this. So actually, it's not true. Let me rewrite this, right? So first of all, why I claim it's actually it's not true, right? So first of all, notice what are we claiming? So we are trying to derive a PDE, right? And with the PDE, the whole idea is the option price is a function, right? This is a deterministic function, all right? It's not a stochastic object. So like, Black-Scholes formula or something like that. So basically, I'm claiming it's a function of T and X, if you will, right? So completely deterministic, except that when I find the stock price, I plug into the X, right? So why is that surprising? It's surprising because, when you look at a exotic option price, right? Let's just look at the look backward Asian, right? There's no way for look backward Asian at any point to only be a function of T and ST. That's just impossible. Why? Because at any time like this, you must know what the running max is doing before you can price the option at this time, right? At any time like this, the value of the option must depend on the whole max up to that time. You understand? Like this, right? So this is impossible. So it must depend on this too, right? Because the option is priced based on these values. At any time before that, it must be based on these values up to that time. Okay. Now, so when I say that for the up and out, which is the barrier options, that is this case, then actually that's not true, right? What happens is this with another object, indicator function, that, so hold on. This is actually not true. The precise statement is as long as you're still in the game, then you are a function only of T up to that time. All right. So I'm simplifying things here to kind of show you what we are kind of trying to talk about. But the true equality is like this. In other words, right, what I'm trying to say is for up and out call, as long as you know that you have not crossed yet. So this is where the path dependent comes in. All right. This is where the path dependence comes in. As long as you know that you have not crossed the path yet, okay, then, right, to look at the value itself, all you have to do is look at the current stock price, and you don't need to look at the whole past history. Okay, so as long as the barrier has not been crossed, the value of the option can be determined only by the current stock price. Again, this might seem very simple to state, but as we discuss the other kind of options, you will see, right? That in general, a exotic option depends more on just the current stock price. It depends on the whole history of the stock. All right. For the barrier option, the history is buried in here. In other words, that as long as the path has not been, the barrier has not been crossed, then to decide the up and out call, you only need the current stock price. Why is that true? Because it's a call to begin with, right? It depends on only the future S big T. That's why you only need the current S little t to decide S big T, essentially. Also, right, what happens if this is false? Meaning if tau is less than t, what happens? If this is true, what that means is, right, the barrier has been crossed before t. But if the barrier has been crossed before t, then this will be 0. Then doesn't matter what this guy is, this will make it also 0. So therefore, this actually is a true equation in general. So this is a precise equation. It's true whether this is true or false. If this is true, then we can forget this and we just use ST to determine the future value. If it's false, then this is still a non-zero function because it's a deterministic function. It cannot turn magically to 0. But this will turn it off. This will make the whole thing 0, and this guy will be 0 over here. All right, so this is not quite true, right? But it's just trying to emphasize that point. So, all right, so let me quickly write down the PDE and we'll explain it next time again, right? So the PDE for up and out call will turn out to be V sub t plus V sub x Rx, or Rs, whatever you want, right? Let me do Rx plus 1/2 V sub xx sigma square S square x square minus R times V is equal to 0. Right? This is for 0 less than equal to t less than equal to t. Surprise? Can this be true? It cannot be true, right? Because this is what kind of PDE? This is the Black-Scholes PDE for European call, right? If the up and out call has the same as the Black-Scholes, that means that up and out call option will be same as European call option, right? That cannot be true. Plus, right, there's no barrier shows up here, right? So that cannot be true. So what makes it true? What makes it true is boundary conditions, which does not shows up in Black-Scholes PDE. The boundary condition is this, right? T is between 0 to t, but this is only true for x between 0 and L. Remember, right? X here stands for our stock price. Or X is really ST, all right? So you only care for this. Moreover, the value at any time and when the stock has hit L will be 0. All right, so let me tell you what it is. So basically, right, I'm not sure you have seen it in numerical analysis yet, but in the TX domain, sorry, yep, in a TX domain like this, right, you will have L, right? Here's T. You only solve your PD in here. And this is exactly where I was talking about custom code, what that Kareem asked, right? So PD is only solved in here, where you have that on this boundary, the PD is 0. And on this boundary, the PD is x minus k plus. All right. So you have these two boundary conditions, and you solve for the PD inside this domain, from which you get VTX for any time t and little x, from which you can plug in the stock price, right? So you ask, what about here, right? Here, automatically V is 0 because the stock has been above the barrier, right? So this above here is 0. Out here is irrelevant because that's beyond expiration. So therefore, the entire domain is here, right? This is 0. Of course, right, before here, this is the past. Down here cannot happen because the stock is always positive. Okay, so this makes the whole big difference between the Black-Scholes and the up and out call. All right, we want to be on time a little bit. We'll pick up this discussion again on Thursday. All right.
Thank you, Professor.
Yep. All right. Thanks. Yeah. Thanks.